problem we want to solve this week is as follows. We're given a triangle ABC where the side opposite vertex A has length lowercase a, the side opposite vertex B has length lowercase b, and the side opposite vertex C has length lowercase c. And we're going to do a construction that allows us to bisect the angle at vertex A and ultimately we're going to do a construction which leads us to a point F on the side BD, and we're going to want to show that the ratio of the length from B to F over F to C is the ratio of these cubes of these side lengths. Now, before we can understand the question and before we can solve the problem of the week, let's review some properties about angles and triangles, which will be helpful in solving this problem. These are the 5 properties of angles and triangles which I want to review before solving the problem of the week. The first one I'm going to go over, I've labeled it last. It's called the law of sines. You don't need to know any trigonometry to solve the problem of the week, but if you do happen to know the law of sines, it can be used to give us an alternative method for solving this problem. In addition, it is useful for understanding how to explain property number 2 and property number 4. Recall that the law of sines relates the angles in a triangle to the sides opposite in this way. So the sine of alpha over its opposite side is equal to the sine of beta over its opposite side is equal to the sine of the third angle over its opposite side. And this is always true for any triangle. And this is a common way to write the law of sines. And if we think about it, these equations can be rearranged. For example, if we look at this bottom set of equations here, we get this left-hand equation can be rearranged this way if we leave the b in the denominator here and the sine of alpha in the numerator here, and then switch the a and the sine of beta like this. This equation is equivalent to this equation. We can see that's true because each of these equations cross multiplies to the same thing. B times sine of alpha is a times sine of beta. B times sine of alpha is a times sine of beta. So we can rewrite this equation this way if we want. And similarly, we can rewrite this equation this way. And we can do that for all the angles. So we can take the ratio of the sines of the angles is equal to the ratio of the corresponding opposite sides. It's not difficult to show where the law of sines comes from. We can drop a perpendicular from any vertex of my triangle down to the base, and this is the height of my triangle. And then the definition of the sine, we have sine of beta is its opposite over its hypotenuse, which is h over c. And we also have the sine of gamma is the opposite over the hypotenuse for gamma, which is h over b, so the sine of gamma is h over b. And solving for h in these two equations, it gives us that on the one hand, h is c times the sine of beta from this equation, but on the other hand, h is b times the sine of gamma. From the second equation. And now we can divide both sides of this equation by b and by c, and that gives us the sine of beta over b is equal to the sine of gamma over c. That one. And this is true for any two angles, beta and gamma, in my triangle. Even if one of the angles is obtuse, this still works. To see why that's true, it's helpful to recall that the sines of supplementary angles are the same. So the sine of any angle alpha is the same as the sine of 180 minus that angle. And so knowing this helps us to understand why the law of sines works, regardless of whether the angles alpha, beta, and gamma are acute or if one of the angles is obtuse. Again, we don't need to know the law of sines to solve the problem of the week, but it does give us an alternative method of solving if we do know it. In order to understand the written solution, we do need to know these first four properties. So let's review these four properties next. The first of these properties is the alternating interior angle property for parallel lines. Let's recall, this property looks like this. So the property for alternating interior angles for parallel lines goes like this. If two lines are parallel and we have one transversal, then these alternating interior angles must be equal. And this is not too difficult to tell if you can remember that any two vertically opposite angles must be equal. And then we can see, because this is parallel to this, and this line is parallel to itself, that these angles must be equal. Notice if I have two lines that are not parallel and a transversal, then the alternating interior angles will not be equal, like this. The second property on our list tells us how to relate the side lengths of a triangle to its interior angles, like this. So the second property tells us that the shortest side of a triangle is always opposite the smallest angle, and that the longest side of a triangle is always opposite the largest angle. Or if alpha is less than beta is less than gamma, then the corresponding opposite sides, A is less than B is less than C. And if any two of the angles are equal, then the corresponding opposite sides are equal. This property can be proved using the law of sines. I can show you a sketch of the proof. It looks like this. So first of all, if you take any two angles in your triangle, and if alpha is the smaller one and beta is the greater one, it follows that the sine of alpha must be less than the sine of beta. Now, if alpha and beta were any two arbitrary angles, this is not necessarily true, that if alpha is less than beta, the sine of alpha must be less than the sine of beta. But it must be true, it is true, if alpha and beta are the interior angles of a triangle. It takes some thought to show this, but if you believe that, then the chain of thought goes like this. If alpha is less than beta, then the sine of alpha is less than the sine of beta. Then the law of sine says that A over B is the sine of alpha over the sine of beta. And because the sine of alpha is less than the sine of beta, the sine of alpha over the sine of beta must be less than 1. And therefore, it follows that A over B is less than 1, which means that A is less than B. And so this is what the proof would look like if you want to prove that if the angle alpha is smaller than the angle beta, the side opposite, A, must be smaller than this side opposite, B, and equality would follow here if we have equality of the angles here. The third property that we want to recall, in order to understand the written solution, is we need to remember how similar triangles work. And that goes like this. Similar triangles are ones that share the same set of interior angles. For example, in this picture, my larger triangle with side lengths big A, big B, and big C is similar to my smaller triangle with side lengths little a, little b, and little c, because each of these triangles shares the same set of interior angles, alpha, beta, and gamma. Alpha, beta, and gamma. And so what happens in this case is that one of the triangles is a scaled up version of the other. So if this is side length A, then this corresponding side length is a multiple of little a. For example, this larger triangle looks like maybe R is 2, because maybe this larger triangle is about 2 times as large as this smaller triangle. And so this corresponding side, big B, is the same multiple, R times little b, and this corresponding side length, big C, is the same corresponding multiple of the side length, little c. And the scaling factor R could be, for example, in this picture, R looks like maybe it's 2, or the bigger triangle could be 10 times as big as the smaller triangle, so R could be 10, or the bigger triangle could be 100 times as big as the smaller triangle, and then R would be 100, or R could be 1.1, and if the scaling factor R is 1, then the triangles are exactly the same size, so not only are the triangles similar, but in fact they're the same, so they're congruent in that case. And the similar triangles is generally written this way. So that we can see that my common scaling factor R can be achieved by dividing big A over little a, because that would be little RA over little a, which is R. It's also big B over little b, and similarly, it's big C over little c, because big C over little c is r. So you take the side, which is opposite alpha in the big triangle, and divide it by the side opposite alpha in the little triangle, or big A over little a, and that will be equal to the side opposite of beta in the big triangle over the side opposite of beta in the little triangle. And that will equal as well the side opposite of gamma in the bigger triangle, big C, over the side opposite of gamma in the smaller triangle, or little c. And this is the common way of writing similar triangles. And with some thought, we can see that we can also write these equations this way. So this equation here can be rewritten this way. So looking in the big triangle, the side opposite of alpha in the big triangle over the side opposite of beta in the big triangle is the same as the side opposite of alpha in the little triangle over the side opposite of beta in the little triangle. And the same for all the other corresponding sides. So big B over big C is little b over little c. When we're comparing the corresponding sides in the big triangle to the corresponding sides in the small triangle. And comparing these equations is the same. Big A over big C is the same as little a over little c. If we rearrange this equation, we'll get this. So that's two ways to write down the ratios for similar triangles. You could take the ratio of two sides opposite of the same angle and equate them. Or you can take the ratio of two sides in the same triangle and equate that to the ratio of the corresponding sides in the other triangle. We have one more property of triangles which we need to review before we're ready to solve the problem of the week, and that is the angle bisector theorem, and that looks like this. So the angle bisector theorem goes like this. We have a triangle, and we've bisected one of the angles like this, so that this angle is the same as this angle, is half of the original angle. Then these corresponding sides are related like this. There are two ways we can look at it. We can say D is to C as E is to B. So we can take the ratio of the sides D over C in one half of this triangle and take the ratio of the corresponding sides E over B in the other half of this triangle, and they are equal. We can rearrange this equation by fixing the D in the numerator and the B in the denominator as before, and interchanging the C and the E here, and we get a new equation with the same cross product. So this is equivalent to this equation. And that says that if I compare the sides in the two corresponding halves, we have D over E is C over B, like that. This is very easy to see why this is true if you know the law of sines. So you don't need to know the law of sines in order to be able to use the angle bisector theorem, which is a handy theorem to use, but if you do understand the law of sines, it's easy to explain this theorem like this. So we have D is opposite the angle alpha over 2. and E is also opposite the angle alpha over 2, and C is opposite this angle here. Let's call it theta. And B is opposite of 180 minus theta. So the law of sines says that D over C is equal to the ratio of the sines of the corresponding angles. D is opposite alpha over 2, and C is opposite theta. So D over C is equal to the sine of alpha over 2 over the sine of theta, and then recalling that the sine of theta is the same as the sine of 180 minus theta. So replacing the sine of theta in this ratio here with the sine of 180 minus theta, we have that D over C is equal to this ratio, but the law of sines again says that the sine of alpha over 2 over the sine of 180 minus theta is the ratio of the corresponding sides, or E over B, because E is opposite of alpha over 2, and B is opposite of 180 minus theta. And so we have D over C is E over B, and the claim is proved. And that's how the angle bisector theorem works. Now that we've reviewed these 5 properties, we're ready to draw the triangle, understand what the problem is asking, and use these properties to solve the problem. Now that we have reviewed some of the properties of angles and triangles, we are ready to understand what the problem of the week is asking and then solve the problem. So we have a triangle ABC like this, with corresponding angles alpha, beta, and gamma, and the side length opposite the vertex A is of length A, and opposite the vertex B is of length B, and opposite the vertex C is length little c. And in this triangle, I've made the angle beta larger than the angle gamma. And after I've shown how to solve the problem, I will show how this doesn't matter and that the answer is going to work out the same if I make the angle beta smaller than the angle gamma, or if beta and gamma are equal. And the problem asks us to make the bisector from A to D of the angle BAC. So I'm going to bisect this angle alpha like this. And then this point here is my point D, so that AD bisects alpha into 2 equal halves, alpha half and alpha half like this. And I notice from my picture that things aren't symmetric because this angle is larger than this angle, and so the D is a little bit over to the left like this. And I can verify that mathematically that's really correct as follows. So I can recall the angle bisector theorem, which gives us this, so that this length BD over this length DC is the same as C over B, like this. And then I recall property number 2, the relationship of the side lengths to the angles in a triangle. And because C is opposite the smaller angle gamma, and B is opposite the larger angle beta, we know that C is the smaller of the two sides, C and B. So C over B is a ratio which is less than 1, like that. But then because C over B equals BD over DC, then it follows that this ratio is less than 1, which means that multiplying both sides of this inequality by DC, we have that BD is the smaller length. So BD is smaller than the length DC. So this length is smaller than this length, which is what my eyes are telling me in this diagram. And what's that telling me is that when I'm being asked to find the midpoint, because this is the smaller length, I know that the midpoint is to the right of my point D, right over here, like this. And then when we're asked to find E, which is the point symmetric to D with respect to the midpoint, so we're going to reflect D across the midpoint symmetrically to this point over here, so that this length dm is the same as this length me, then I know that E is to the right of M, which is to the right of D. And then we're asked to find the point F so that angle EAC is the same as angle BAF. And angle EAC would be from E to A to C, like this. So here would be my angle EAC. I'm going to call it alpha, beta, gamma. What's the next letter up? Delta. Just to give it a name, I'm going to call it delta. And what I know about this triangle is that because E is to the right of D, I know that my angle delta is smaller than this angle, which is half of alpha. And so when I'm asked to find another angle, BAF, so I'm trying to find BA and where's F, where that angle is equal to delta, then I know that my point F is going to be over here to the left of D, like this. So F needs to be the point where this angle, let me draw it in, there's my angle BAF, needs to be delta. It needs to be the same as this angle. And because I know that delta is smaller than half of alpha, that makes that my F has to be the left of D, like this. And what we're being asked to show is that this length BF over this length FC, it's similar to the angle bisector theorem, where BD over DC was C over B, only this time it's going to be BF over FC. It's going to be C cubed over B cubed. And now that we understand what the question is asking, we can use the properties of angles and triangles to show how to solve the problem, and to show how that BF over FC is C cubed over B cubed. And that goes like this. So in order to solve this problem, I'm hit all of a sudden by a mathematical inspiration to draw in all of these extra lines here that will give me several sets of similar triangles, which I can then use to solve the problem. And if you don't like this inspired approach, then after I'm done showing you how to understand the written solution, I can show you an alternative solution which uses the law of sines to solve the problem, and then you won't have to draw in all of these extra lines. But what we've done here is we've taken our triangle ABC and we've drawn the other half of the parallelogram that it belongs to. So this side here is parallel to the side AB, and this side here is parallel to the side AC. And then I've extended the segment AE all the way to here, to the point S on this parallel side, and I've extended the segment AF all the way to here, to the point T on this parallel side here. And what this is going to do for us is it's going to give us three sets of similar triangles, this pair of similar triangles, and this pair, and this pair, which will allow us to solve the problem. And I'm going to go over each of these cases one at a time. Before I do that, I'm going to make a couple of observations that are going to help me out along the way. And the first observation is to keep track of what was going on with this construction. And because M is the midpoint of this side BC, we know that this length BM is the same as this length MC. And also because of the way D was reflected across the midpoint symmetrically to get E, we know that this length DM is the same as ME. And with these two together, we get these two observations, which we're going to need. We're going to get BE, which is the halfway distance plus this length, is the same as if I come from the other side and do this halfway distance plus this same length, which is DC. So BE and DC are the same. Or I could subtract this length off. So I can get this one if I take the halfway distance and subtract this bit, I get BD, which is the same as if I take this half distance and subtract this same length and get EC. So BD is the same as EC. My second observation, we've already noticed this before. This comes from the angle bisector theorem. Because the angle BAC was bisected by the segment AD, so that this is half of alpha and this is the other half of alpha, and so that we know that BD over DC is the same as C over B here. And then from observation number 1, we're going to find out later we're going to need this as well, because BD is the same as EC, and DC is the same as BE. Then C over B is not only equal to BD over DC, but it's also equal to EC over BE. So EC over BE. The next thing let's observe from property number 1 in my properties of angles and triangles, or the alternating interior angle property, because I have two parallel lines here and a transversal, and so these two alternating interior angles here are the same. So if this is gamma, that means that this is gamma right here. And we also have this pair of parallel lines here and this transversal. And so these alternating interior angles here must be the same. And so that if this is beta, this is beta. And now we're ready for our last three observations, which we can make because of our similar triangles. So the first pair of similar triangles I find here, and I know that these are similar because I know that this angle is the same as this angle because vertically opposite angles are equal. And this is gamma, and this is gamma. And so this small triangle contains the same three angles as this larger one. We have gamma, and this angle here, and then the remaining angle, which must be 180 minus gamma minus this angle for each of these triangles. So this angle here is 180 minus gamma minus this angle, which, by the way, we don't need to know that, but I notice that this is alpha minus this small bit delta right here. And so observation 3 is, looking at this pair of similar triangles, we have the side opposite of alpha minus delta in the small triangle, which is BF, over the side opposite alpha minus delta in the large triangle, which is FC. And this ratio must equal the side opposite this angle here in the small triangle, which is BT, over the side opposite that same angle here in the large triangle, which is this side, which is B. And this is one of the steps that we're going to need to use to show that this ratio BF over FC, our ultimate goal is to show that this is equal to C cubed over B cubed. And this is how far we've got at this point. So we need to look at a few more similar triangles so that we can put all of these together and get the result. So for my fourth observation, my second pair of similar triangles looks like this. And I know these are similar because they share three common angles. I have beta plus gamma here and beta plus gamma here. And I have delta here and delta here. And the third angle must also be the same here and here. it must be 180 minus beta minus gamma minus delta, which we don't need to know this, but that would be alpha minus delta again, because 180 minus beta minus gamma is alpha. And so from this pair of similar triangles we're getting, we take the side opposite delta in the left-hand triangle, gives us BT, and the side opposite delta in the right-hand triangle gives us the side length CS, and this ratio is equal to the side opposite alpha minus delta in the left triangle, which is C, over the side opposite alpha minus delta in the right-hand triangle, which is B. So we have BT over CS is the same as C over B. And we have one more pair of similar triangles that we can exploit, and that will be observation number 5, my last observation. And my observation number 5 is similar to observation number 3. I have this pair of similar triangles here. I know that this angle is equal to this angle because vertically opposite angles are equal. And then these two triangles also share the same angle beta right here. And because these two triangles share the same two angles beta and this angle, it follows that the third angle, which is 180 minus the sum of those two in each case, must also be the same, and that these triangles are similar. And again, we didn't need to know it, but as we can see from this diagram, that third angle must be alpha minus this little angle delta here. So this must be alpha minus this little angle delta here. And so we have for observation number 5 from this pair of similar triangles, we look at the side opposite this angle here in the small triangle is CS, and the side opposite the same angle in the larger triangle, which is this side, which is C, and this ratio is equal to the side opposite alpha minus delta in the small triangle, which is EC, over the side opposite alpha minus delta in the large triangle, which is this side, BE. So we have that CS over C is the same as EC over BE. And now we've put together all the observations that we need in order to solve the problem. And that goes like this. So we're now ready to prove that the ratio BF over FC is C cubed over B cubed. And we do it like this. We start out with observation number 3, which, recall, came from this pair of similar triangles here. The ratio BF over FC is 1 over B times the side length BT. And then observation number 4, use this pair of similar triangles here. BT over CS is C over B. So multiplying both sides of this equation by the side length CS, we can solve for BT, and we replace BT in this expression. BT is C over B times CS, right here. And finally, we're ready to use observation 5. That came from this pair of similar triangles here that says that the side length CS over side length C is equal to side length EC over BE. So from here to here, we have C over B squared here, and then we replace CS. CS gets replaced with little c times EC over BE, because we can solve for CS from here by multiplying both sides of this equation by little c. And so now we have c squared over b squared here, but EC over BE can be replaced with C over B by observation number 2. As we recall, that EC over BE is the same as C over B. And we've got it. The ratio BF over FC is C cubed over B cubed. Now we can wrap up just a couple loose ends, and we'll be finished. So recall last time that I observed that I made my angle beta larger than gamma, and I claimed that it didn't matter, and we're going to get the same result if beta happens to be smaller than gamma, or if beta equals gamma. I can explain that this way. Let's just take this same triangle and swap the labels around. So instead of calling this B, let's call this vertex C, and let's call this vertex B instead of calling it C. And now the angle on vertex C is larger than the angle on vertex B. But that would require that we label the side opposite vertex C as little c, and the side opposite vertex B is little b. But that doesn't change the fact that what we just proved is that the ratio of this length to this length is this side length cubed over this side length cubed. I've just relabeled all of those sides. So the equality that we just proved says this. It says that this length, which is FC, over this length, which is BF, is the same as the cube of this length over the cube of this length, which now becomes B cubed over C cubed. And so, if I take the reciprocal of both sides, we still have that BF over FC is C cubed over B cubed. So this result is still true. And it didn't matter if I made the angle on the vertex C the larger one, and the angle on the vertex B is the smaller one. Or if you like, it didn't matter if I put the smaller angle on the left and the larger angle on the right. And finally, what happens if beta equals gamma? And that's the easiest case, because in that case, what will happen is that if beta equals gamma, then when I draw my bisector, all of my points, F, D, M, and E, will collapse to the same point, and my picture will look like this. So if beta equals gamma, then I have an isosceles triangle here, and so these two halves of the triangle share the same angles, beta and alpha half, and this will be 90, because these two angles have to be the same, and this triangle will be congruent to this triangle, which means that this length is equal to this length, which means that D happens to be the same as the midpoint, M, and so if I reflect D across the midpoint, it will reflect to itself, E, and the angle delta will be just alpha half, and so that F will be the same as D. So the ratio BF over FC, but F will be the same as D, so this will be the same as BD over DC, but BD and DC are equal, so that ratio is 1. And again, by property 2 of the angles and triangles, because these angles are equal, the opposite sides, C and B, will also be equal, so little b will equal little c, which means that c cubed over b cubed will be the ratio c over b cubed. But since c and b are the same, c over b is 1, so c cubed over b cubed will also be 1. And so in the case when the angle at vertex B is the same as the angle at vertex C, this is actually the easiest case to solve, and we still get that the ratio BF over FC is C cubed over B cubed, because the ratio will just be 1 in that case. And the problem is solved. For an alternative solution, I will next show you how to solve the problem without having to draw all of these extra lines. So if I don't feel mathematically inspired to draw all of those extra lines, I can still solve the problem. And in that case, one way to do it is to use the law of sines. So I will show you how to do that next. As an alternative solution, we can go back to the original triangle that we constructed, and without drawing any extra lines, we can use the law of sines instead to solve the problem, and to show that the ratio BF over FC is C cubed over B cubed. In order to accomplish this, my plan is to apply the law of sines to 6 of the triangles in this diagram. This one, this one, and this one, and correspondingly, going from right to left, I will apply the law of sines to this triangle, and to this triangle, and finally to this triangle. Before I do this, I need to label these angles here as follows. I'm going to use the fact that the sum of the original three angles, alpha at vertex A, beta at vertex B, and gamma at vertex C, add up to 180 degrees. Alpha plus beta plus gamma equals 180 degrees. Then looking at the angles in this triangle, I know that those have to add up to 180. I have beta here, so I need alpha and gamma, and then I need to subtract delta to make that work. So this angle here is alpha plus gamma minus delta. So that when I add these three angles, I get alpha plus beta plus gamma, and minus delta plus delta cancels, which just gives me alpha plus beta plus gamma, which is 180. Now how to calculate this angle? Well, one way to look at it is that this is 180 minus this angle, but 180 minus this angle is just beta plus delta. So this must be beta plus delta. Right? If I add alpha plus gamma minus delta plus beta plus delta, I do get alpha plus beta plus gamma, which is 180 again. Now to get this angle, I look at my picture and I remember that this angle was bisected, so this total is alpha half, and then what's left is alpha half minus delta. So I know that this is alpha over 2 minus delta, and so the angles in this triangle here, AFD, they have to add up to 180, and so far I have alpha half and beta. The delta minus delta cancels, so I need one more alpha half and a gamma. So that means that this angle is alpha half plus gamma, so that these three angles add up to alpha half plus alpha half, which is alpha, plus beta plus gamma, and the deltas cancel. So I'm getting alpha plus beta plus gamma, which is 180. And this angle, I know, is 180 minus this angle, which is the same as this angle plus this angle. So this angle is alpha half, or 1/2 alpha, plus beta plus delta minus delta. So this angle is just alpha over 2 plus beta. And finally, like before, this angle we know is half of alpha minus delta and then we know that in triangle ADE, these angles have to add up to 180. So far we have alpha over 2 plus alpha over 2, which is alpha, and then plus beta. So we have alpha plus beta, and we have minus delta, so we just need to add gamma and delta. So this is gamma plus delta, so that these three angles add up to 180 because we have alpha half plus alpha half, which is alpha, and then plus beta, and then plus gamma, and the delta minus delta cancels. So we have alpha plus beta plus gamma, which is 180. I'm almost done labeling all of these angles. I have one angle left that I need to label, this one, which is 180 minus this one, which is the same as this plus this. So if I add these two angles together, I have alpha over 2 plus alpha over 2, which is alpha, plus beta minus delta. So I know that this angle is alpha plus beta minus delta. And that makes sense because these three angles need to add up to 180, and they do because I have alpha plus beta minus delta plus delta, which is 0. So I have alpha plus beta plus gamma, which is 180. And now that I've labeled all of the angles which I need to use, I'm ready to apply the law of sines to my 6 triangles, and I will do that like this. So for my first triangle, that's triangle ABF, I have that this side length BF, which is opposite delta, we get BF over the sine of delta is equal to this side, C, over the sine of this opposite angle, but this is alpha plus gamma minus delta. Continuing to my next triangle, which is triangle ABD, I'm doing the same thing. So I take side BD over the sine of its opposite angle, which is alpha over 2, and that's equal to C over its opposite angle, so C over the sine of alpha over 2 plus gamma, like that. And working my way from left to right, I have one more triangle to do on this side, and that is triangle ABE, like this. So we have that C over the sine of its opposite angle, which is gamma plus delta, so C over the sine of gamma plus delta is equal to this side, BE, over the sine of its opposite angle, which is this angle here, which is the total alpha minus delta. Now I have 3 more triangles to look at on the right-hand side of this diagram. So the next triangle I'm looking at is triangle AFC, like this. And when I look at this triangle, we have this side length FC, which is opposite this angle, which is the total alpha minus this bit, so this is alpha minus delta. So we have FC over the sine of alpha minus delta equals this side over the sine of its opposite angle, which is beta plus delta. So we have B over the sine of beta plus delta, like this. Continuing to work my way to the right, my next triangle will be triangle ADC, like this. And for triangle ADC, I take my side DC, which is opposite this angle, which is half of alpha. So DC over the sine of half of alpha equals B over the sine of this angle. So B over the sine of half of alpha plus beta, like this. Continuing to work my way to the right, I have one more triangle that I want to apply the law of sines to, and that will be triangle ACE, like this. And for this triangle, we are getting this side EC over the sine of delta is equal to this side B over the sine of this angle, alpha plus beta minus delta, like this. And now I have all the ingredients I need to prove that the ratio BF over FC is C cubed over B cubed, and I accomplish that with the following steps. So from my 6 equations, which I got from my 6 triangles and the law of sines, I'm going to start out with these first 2 equations at the top, numbers 1 and numbers 2. And I'm going to look at these equations here. And I see that I can solve for the ratio BF over FC because I can solve for BF in this equation and FC in this equation, like this. So the ratio BF over FC, which is the ratio I seek, the numerator BF can be solved here by multiplying both sides of this equation by the sine of delta, and so then for BF I get C times the sine of delta over the sine of alpha plus gamma minus delta, which is what I've written here in the numerator for BF. And for FC, I can solve for FC in this equation by multiplying both sides by the sine of alpha minus delta. And when I do that, I see that FC is B times the sine of alpha minus delta over the sine of beta plus delta, which is what I've written here in the denominator for FC. Right here, FC is B times the sine of alpha minus delta over the sine of beta plus delta. And so this equation I got from using equations number 1 and number 2 in my law of sines. Then I can simplify this stack of ratios like this. So this ratio over this ratio is the same as this ratio times the reciprocal of this ratio. And so we will get C over B and the sine of delta over the sine of alpha minus delta, and this part becomes the sine of beta plus delta over the sine of alpha plus gamma minus delta. Now this looks a little bit messy, but then I remember that the sines of supplementary angles are equal, and so there's going to be some simplifying here, if I go back to my triangle, I can see that looking at beta plus delta and alpha plus gamma minus delta, these are supplementary angles. And so their signs are the same. And so that means that this ratio is really just 1. And so this expression for BF over FC simplifies like this. So we get C over B times just the sine of delta over the sine of alpha minus delta. Now I go back to my equations, which I got from the law of sines, to try to figure out how I can replace these quantities. And I see that in this equation here, I'll call it equation 3. So solving for the sine of alpha minus delta in this equation, I get that the sine of alpha minus delta is equal to BE times the sine of gamma plus delta over little c, like this. And so going from here to here in this step, I'm using equation 3, like this. And now I'm going to simplify this stack of ratios, like this. And I'm almost done. So this stack of ratios simplifies to c squared over b, and then I have the sine of delta in the numerator and be times the sine of gamma plus delta in the denominator. And finally, I'm going to go back to my 6 equations, and I'm going to find a way to replace the sine of delta by using this equation here. I'll call it equation number 4, and in this equation I will solve for the sine of delta, and so this expression becomes c squared over b, and I have be sine of gamma plus delta in the denominator, and the sine of delta comes from here. When I solve for the sine of delta, I get EC over B times the sine of alpha plus beta minus delta, like this. And so going from here to here, I used equation 4, like this. I'm almost done. I'm now going to simplify this stack of ratios, like this. And so now I have that BF over FC is this expression here, which simplifies to, I have c squared in the numerator, I have a b and another b here in the denominator, so I have c squared over b squared right here. Then I have EC in the numerator and BE in the denominator right here. And what's left? I have the sine of alpha plus beta minus delta here in the numerator, and the sine of gamma plus delta in the denominator. And again, because the signs of supplementary angles are the same, this ratio simplifies conveniently to 1, which I can see in my triangle. Okay, because alpha plus beta minus delta, which is this angle, and gamma plus delta, which is this angle, are supplementary angles, so their signs are the same. And so that's why this ratio is 1. So this expression just simplifies to c squared over b squared times EC over BE, like that. And then how I got from this step to this step, I have c squared over b squared, and I replaced EC over BE with BD over DC, similarly the way we did in the previous solution. And this again comes from our triangle. Side length EC is half of this minus this little bit, which is the same as half of this minus this little bit, which is BD. So EC is BD. And that's how I replaced EC with BD. And also, I replaced BE with DC because BE is half of this length plus this little bit, BE, which is the same as half of this length plus this little bit, DC. And that was because M is the midpoint of this length, and because DM is the same length as ME, because D is reflected across the midpoint to point E, as we recall from our construction. So we're almost done. And in my final step, I replaced BD over DC with C over B. And I can do that in two different ways. We did this in the previous solution by using the angle bisector theorem, because BD and DC were the segments that got created from this bisected angle, so that this angle is the same as this angle, and so that BD over DC was C over B from the angle bisector theorem. Or, if you didn't happen to know the angle bisector theorem, you could get it from our 6 equations that we got from the law of sines, because after all, the angle bisector theorem, that's where it came from. It came from the law of sines. So I can get this as C over B. So if I didn't know the angle bisector theorem, I could use these two equations, I'm calling them 5 and 6, to get from here to here. So to get BD over DC, I could solve for BD from this equation, and I could solve for DC from this equation, and I would find that BD over DC is indeed equal to C over B. So this alternative solution does give me, again, that the ratio BF over FC is indeed equal to C cubed over B cubed. And the problem is solved.